For this part, we're starting out with a piece of 304 stainless steel round stock. In order to hold it for the first operation, we're going to dive straight into a set of Saunders Machine Works Mod Vise aluminum soft jaws. So we start out with a 1/4 inch tool conducting a 2D adaptive operation just to clear the area. We follow that up with a 2D pocket to finish the floors. Then we come back with a 2D contour to finish the walls, and a 2D chamfer, just enough to knock the edge off. We're running some pretty conservative aluminum speeds and feeds here, nothing too fancy. For Op 1 of this part, we're going to dive right into a 3D adaptive strategy. Throughout this project, we use a 1/4 inch Lakeshore Carbide roughing end mill. It held up great and really took a beating. After that, we conduct a 2D adaptive operation that we programmed to be 10 thou below this finished edge. The reason why we do this is to give clearance for the finish end mill, and will make sense when we get there in just a minute. Next up, we go with a 3D adaptive strategy for an 1/8 inch end mill. We're going to run this little guy pretty slow and have an optimal load of just 10 thou. We have a programmed axial stock to leave here of just 15 thousandths, but we really need to pay attention to how much is actually going to be left. We'll get to that in a minute too. An important input to note here is the ramp taper angle. We're machining 304 stainless steel, and 304 does not like to be rubbed on. If the flutes of your end mill are contacting the material without actually making a chip, without actually making a cut, then your end mill is going to wear out very quickly. The material is going to work harden, and it's not going to go well. Giving a ramp taper angle gives the helix a cone shape. This is really going to help with chip evacuation, prevent your end mill from rubbing, and ultimately create a lot more reliable cut. Next up, we are going to spot the center hole. For this, we use a 1/4 inch drill mill, and we run it pretty slow. Even with some pretty conservative speeds and feeds, the tip of the tool still chipped. Ultimately, a spot drill or center drill would have done a little bit better, but this got the job done for the one part we were making. This hole finishes at 3/8 of an inch, and we need to hold that to a pretty tight tolerance. So we're going to finish that with a reamer. Before the reamer, we need to get that hole pretty close to the finished size, so we plan on using a number 8 359 high-speed steel twist drill. Because this machine only has a 2 horsepower spindle, we need to drill a pilot hole before we come in with that number 8 drill. For that, we use a carbide 1/4 inch drill running at 150 SFM, feeding at 5 thou per rev to drill all the way through the part. We follow that up with a high-speed steel twist drill, running that a little bit slower at 10 thou per rev, and it worked out great. That being said, I'm not confident high-speed steel is going to last a long time drilling 304 stainless. If we were running a bunch of these, I would certainly want a carbide drill and a carbide reamer. But we came in with a high-speed steel reamer. We ran it at 1500 RPM, 7.5 inches per minute. The hole came out on size, and I was able to breathe a sigh of relief. So now we get into our first finishing end mill to finish the top surfaces of this part. So we decided to use a 2D contour instead of a facing operation to try to avoid some tool marks. We just wanted it to be a continuous tool path and try to create the smoothest finish as possible. Within 2D contour, there's an option to leave stock. You can actually leave a negative value down here as well, up to the radius of your tool. So we're using a 1/4 inch tool here. If we go -125, it's red, but negative 124 works great. This causes the end mill to run across the top of that face, clean up that top surface, just like we're looking for. So if you remember earlier, we were talking about the additional 2D adaptive strategy in order to make room for our finishing end mill. This here is where we need it. So this 2D contour toolpath around the outside of the part would have plunged right into the remaining stock if that 2D adaptive hadn't have already cleared it. When working with a tough material like 304, you really have to be careful with stuff like that because that will quickly scrap your end mill. So before we jump into this 3D spiral toolpath, we're going to take a minute to look back at the 1/8 inch tool 3D adaptive. Within that, we have 15 thousandths programmed for an axial stock to leave. We are using a square end mill to clear an area with a rounded bottom. So if we look at the simulation up to this point, we can see that the bottom of the stock that is still there is flat. This means that there is a lot more than 15 thousandths of stock still there. Therefore, if we jump straight into our finishing spiral toolpath, we're probably not going to get a very consistent surface finish. It's going to wear out our finishing end mill and ultimately not give the results we're looking for. So we come down with a roughing 3D spiral toolpath. All that means is we're still going to leave some stock. We are using a 1/4 inch 4-flute ball end mill, and we have 15 thousandths programmed for stock to leave. This way, the 4-flute ball nose end mill is going to take the beating, clear the remaining material before our 6-flute finishing ball nose end mill comes in to leave the best surface finish possible. So with this initial spiral toolpath, we have a step over programmed of 15 thousandths. But when we get down to our finishing end mill, we're going to go all the way down to a 4 thou step over. We're really happy with the surface finish that this left. These helical tools performed very well and the part looks great. Then for our final toolpath of the first operation, we use a 3D spiral toolpath to create the chamfer on the inside hole. We could have used a chamfer tool. It would have been faster, but we already had a ball nose set up. For only doing one part, we decided to go with a spiral toolpath. After the first operation, we're going to turn the part over, and the important part is that our two sides are parallel. Folks, this is where the real fun begins. So luckily, our piece of round stock was a bit thicker than the final thickness of our part. So we're going to set it up to do a test cut. When I set my Z offset, I set it to where the top of the material would clean up, but the part is still going to be quite a bit thicker than the final dimension. So after that end mill runs, we get out our 0 to 1 micrometer and we measure 2 points. Ideally, these two measurements would come out to be exactly the same. Here, the measurement I took was about 2 thousandths difference, and for what this part is, that is not good enough. I think that the root of this problem started clear back in my setup for Operation 1. I seated it with a hammer. Ultimately, that's pushing the rough saw cut edge against the bottom of my soft jaws. Then the top machined surface is not going to be perfectly perpendicular with the cylinder of my raw stock, and I think it made it that much more difficult to set up for Operation number 2. After we find that the parallelism is out, the fun game begins of trying to get it back. I take the part out of the mod vise, clean everything off, make sure there aren't any chips causing problems, get it back in, seat it, and then we're going to get out an indicator. I run an indicator across the top of the part just to start to try to understand what we're looking at, what we're working with. Once we're ready to take our second test cut, I'm going to adjust the Z offset the same amount that the finishing end mill originally took. So if we look in our original 3D adaptive strategy, we were leaving 5 thousandths of axial stock. Therefore, when we adjust our Z offset, we're going to adjust it by 5 thousandths again. the finishing end mill is going to experience the same cutting pressure and hopefully give nice repeatable results. Going into test cut number 2, I thought we were going to get the parallelism back to pretty close, but I was wrong. After I saw that it was still out by almost 0.02, I knew that for my next try, I was going to need to be a lot more deliberate about what I was seeing with an indicator. Therefore, I went ahead and pulled the part out again. I took measurements in 4 different spots around the part. I wrote them down, cleaned everything off, put it back into the mod vise, and then started indicating. I very carefully, very deliberately tapped on the part with a hammer in different spots to get the indicator to read high in the areas that were thick. I was able to get this dialed in to what I wanted to see, adjust the Z offset by 0.005 again, come back with another test cut. When I took 2 measurements after this 3rd test cut, the reading on the micrometer was almost exactly the same. Just to double check myself, I went ahead and grabbed a different micrometer to take a measurement. I got the same reading, and from there I subtracted where I was from the overall thickness of the part on the drawing, and then used that number to adjust my Z offset and go ahead to dive into operation number 2. Operation number 2 uses the same programming techniques, the same strategies as operation number 1. The tools held up, the surface finishes looked great, and overall we were very happy with how the part turned out. In the end, we were able to get the parallelism of this part to within 0.005. So just for a reference, that's roughly 1/4 the thickness of a human hair. After Op 2 is complete, we are ready to get this part up in the 4th axis. So we made a little fixture for this off camera, but the trick is getting the fixture to spin true in the 4th axis. So a tenths indicator, a hammer, and a little bit of patience goes a long ways. In order to make the outside diameter of this part as round as possible, we decided to turn it in a mill. That is right, folks. We are turning the part in the mill. Fusion 360 has an awesome toolpath for this called Rotary. Rotary toolpath gives you the option to make a spiral toolpath of which you can adjust the step over, and it left a beautiful surface finish. In order to get Rotary to create the toolpath that I was looking for, we had to create a new component in the design side of Fusion. So we called this Rotary blank, and it is essentially just a solid disc to the finished diameter of our part. Then on the manufacturer side, we created a new setup. Within this setup for the model, we selected our Rotary blank. A great feature within Fusion is I can now hide that model, and it essentially still looks the same as if I'm working directly with the actual 3D model of my part. So we did some experimentation and decided that a step over of 0.006 would give us a good surface finish and still keep our cycle time at a pretty reasonable rate of just 50 minutes. After we get the work coordinate system set up on this part, dialed in, we are still going to take a test cut. Folks, anytime you're trying to hold tight tolerances, test cuts are your best friend. So we take the test cut, we measure it, we see where we're at, we know where we're supposed to be, we can make an adjustment from there. With this setup, I was changing the diameter of our part within the stock to leave of the Rotary toolpath. We got it dialed in and hit our tolerance right on. By spinning the part in the 4th axis like we did, the circularity of it is right on. If you measure this with a micrometer, multiple points around that outside diameter, you will get the same reading. Folks, this 4th axis is awesome. After the Rotary toolpath, we are ready to jump into the biggest challenge of this part, machining these little fins. Within Fusion, we've programmed this as a circular pattern. You can get to that under Setup and New Pattern. Within a pattern, you have the option to select a circular pattern, an axis of rotation, an angle of separation, and a number of instances. This worked out really well for what we were trying to do here. So we start out with our 1/4 inch Lakeshore Carbide roughing end mill. We're going to slot in between these fins in order to initially clear some material. I originally tried just coming in with an adaptive strategy, and that long length of cut was giving me a lot of problems and making some horrible noises. In order to conduct a slotting operation between each one of these fins, we start out by creating a sketch and an axis of which we want our tool to be oriented. So we come over here with a trace operation, and for that trace geometry, we select the sketch, and then we have a tool orientation option to where we can select the axes that we created for our Z, and then we just select the inside cylinder for our X axis. From there, we use the axial offset to adjust the toolpath just right to where we're removing as much material as possible without getting into the part. Under our simulation, we can make our stock transparent and really helps get a good idea of where we're at. Next up, we use the same tool to conduct a 3D adaptive strategy where we've created a sketch for our machining boundary that covers the area in between the two fins. We have the same tool orientation option to where we can select the same axes and get a great looking toolpath. After the 3D adaptive with the 1/4 inch tool, we follow that up with a 3D adaptive with a 3/16 inch tool. When you look at the simulation for our 1/4 inch tool, we can clearly see that not all of the material is removed. We can then come back with a 3/16 inch tool, the same strategy, the same geometry, but we're able to select rest machining and from previous operations. 3D Adaptive is so intelligent that it can look at your previous operations and create an appropriate toolpath based off what still needs to be removed. After the 3/16 adaptive strategy, we are ready to jump into finishing these fins. We're going to orient the tool parallel to the fin itself by selecting the side of the fin for our Z axis under tool orientation. So we're going to start out with a 2D contour and still leave a radial stock of 3/1000. We're doing this to clean up the rest of the material left from the adaptive toolpaths. That way our finishing tool experiences a nice consistent tool pressure and will leave the best finish possible. We also found that this first 2D contour was best conducted with 2 step downs, so we're not taking quite as long of an axial depth of cut. Because of the diameter of this tool, the relatively long length of cut, and the properties of 304 stainless steel, this was fairly difficult to get a good surface finish. I did some testing and I was pretty confident about our speeds and feeds recipe going into this, but the geometry of the part gave us some trouble. So on the inside radius of that fin, the end mill experiences a slightly higher chip load and it was causing a small amount of chatter. If I could go back and do it again, I would spend some time experimenting with the feed optimization feature and try to get rid of that small chatter. Overall, the finish still looks great and we'll remember that for next time. After the 2D contour, we come back with a 2D trace operation in order to accurately machine the bottom radius around the flange. As you can see, a 2D toolpath is just not going to accurately machine these features. Under a trace operation, we selected the bottom edge of that radius for the curve selection. This created a toolpath that accurately machined that radius around the bottom of the fin. Again, we got just a small amount of chatter on that inside radius, but overall we were very happy with the surface finish on these fins. Last but certainly not least, we dive into the 3D surfacing of this part between the fins. In order to do so, we use a 3D parallel toolpath and 1/8 inch ball nose 4-flute end mill. We were able to use the same sketch and the same axes for tool orientation that we used earlier for our adaptive toolpath. In order to get this parallel toolpath to look exactly the way we wanted, we were able to use one of Fusion's latest updates, Toolpath Trim. What this allows you to do is to define a boundary for your toolpath to avoid. So we'll just do a little example here. We sketch a boundary, hit OK, the toolpath regenerates and avoids that area. This is really helpful to really get the toolpath dialed in just the way you want it. So we'll hit Control Z to undo that and then talk about why we decided on 3D parallel. While conducting tests for this part, I experimented with several different 3D toolpaths. Ultimately, I found that reducing the quantity of axes moving at any given time was going to give the best surface finish possible. So folks, even if you're dealing with a much more expensive, higher end machine, the machine is still not perfect. So it is generally a good programming practice to choose a toolpath that reduces the number of axes moving. For this geometry, we can clearly see that 3D parallel does that for us by watching our simulation. The toolpath is moving multiple axes as it comes up and over and re-enters the cut. But we can see here under our Info tab, we'll slow the simulation down and play. It is only the x-axis that is moving while the tool is in the cut. Ultimately, this worked great. It left a beautiful surface finish, and we are very happy with how the part looks.
I thought Jeffrey did an absolutely awesome job, not only on the part, but on the process and showing how he got to that end result. It's also a great example of it's the carpenter, not the tools. I was blown away with how this part came out on the MX, and it's what Jeffrey spent a lot of his time doing for Proven Cut, showing what you can do with a machine tool, whether it's a small benchtop hobby router all the way up to 20,000 pound vertical machine. How do you run that reamer, that high-speed steel? How do you run that tap? How do you cut stainless? So if you haven't checked out Proven Cut, please go check it out as a video speeds and feeds service. Otherwise, folks, hope you learned something. Hope you enjoyed. Take care. See you soon.